So hello everyone, I'm Hongming. Thanks for everyone for coming here. And so let me introduce my professor, Martin. Yeah. And okay, I'm going to talk about our recent work, Replay Memory as an empirical MDP, combining conservative estimation with experience replay. It's a joint work with Chen Jun, Han Wang, JJ, Boshi, and Martin. And it's also a work done while I'm an intern at Huawei. Yeah. Okay. Okay, so let's start from the paradigm of deep reinforcement learning. So the paradigm of deep reinforcement learning is that an agent's interaction with the environment and learn from the experience here. So usually an agent first interacts with the environment, it takes actions and receives the state and reward. Usually to improve the sample efficiency, there is a replay memory that we store the transitions into it. And then we sample batches of data and update the policy. So we just repeat these procedures again and again until we get a good, maybe optimal policies. Yeah. So we can model this process as a Markov decision process. That state is the state space, A is the action space, and there's a reward R and the dynamics P and the initial state distribution low and the discount factor gamma. So objective here is to maximize the expected accumulative reward. And usually we will use the Bellman optimal equation as an iterative update, such as in DQN, like this. So when we update, we just sample a batch and update the Q network, use this formula. Yeah. So usually we just say there are 3 steps, right? We interaction and we store transition and then we update the policy. So in this work, our most focus is how to sample the data and update the policy. Usually we just call it experience replay method. Yeah. There are some motivations since there are many works that do something about experience replay. Since it is very important for the sample efficiency. We summarize 3 kinds of methods. The first one is reweighted experience replay. This kind of method most focus on how to sample the transitions. So they will not sample the transition uniformly. They will say, yeah, some transition may be more important, so we sample it more frequently. So there is different probabilities for each transition. So how to measure the importance? There are many ways. For example, we can use the TD errors to measure the importance. We can also use the accuracy of the target value. And even we may say that the transition that is collected by the most recent policy is more just important because it's more like on policy transitions. Yeah. And the second way is that episodic RL. Usually when we learn a policy or we update the Q network, we will use TD learning. But this also just say the TD learning is not so efficient than the supervised learning. So when we have many transitions, we can just remember the best value we have met into a dictionary or into something. And when we want to update the Q network, we can just query the dictionary to get the best value we have ever made and just update the Q network in the supervised learning. They say, yeah, will be more efficient. And the last one is reverse update. The reverse update just think when we update the neural network, if we want to get an accurate value estimation for S1, maybe we first need to have the accurate estimation for the S2. Like we first need to have the accurate target value, and then we can get the accurate estimation. So this kind of method just sample a whole episode, and then when they do the update, they just update in a reverse manner to just from the ST and then ST minus 1, just then to the S1. Yeah. So with all of this method, can we do further? So we can know all of this method just want to update the neural network more efficient. But how to do this? They want to do some value estimation, and this all of the ways want to do the value estimation efficiently. So we will think, is there a way that we can do it just better? Yeah. I think just one shortcoming for all of this method is that they treat the transitions individually, or they just treat the individual trajectories. But in fact, maybe there are some trajectory that can interleave together because there may be some state that is similar or the same in different trajectories. So here I draw two trajectory, like maybe this state is just the same, so the two can just trajectory can just merge together. So what we do is that we can consider all the transitions in the replay memory together, and based on this, all the transitions, and we can get a better estimation. Yeah. So yeah, this is the overview of our method. So first, we consider the replay memory as the empirical MDP. We call it RM-MDP, just replay memory MDP. And the MDP is constructed with only existing data. Like there is the replay memory, and all of this data can just construct the MDP. So this is a new MDP, it's an empirical MDP. This is smaller than the original MDP, but maybe we can get a better estimation from this empirical MDP. So the second step is that we can solve this empirical MDP and get a conservative estimation that's considering all existing transitions. We call it conservative. That is because the replay memory can only contain limited data, limited transition. So there may be some actions that is not included in the replay memory. These actions may be good, maybe bad, whatever. But yeah, what we say it is conservative. Yeah. And the final step is that we can use the estimation from this empirical MDP and use this one to regularize the online learning. Yeah. So we can find the only difference is that we just change this replay memory to this structured replay memory. Since the structured memory can form the MDP. Yeah. So we call our method CEER, just conservative estimation with experience replay. And there are 3 steps here. The first one, we just build a directed graph to construct the RM-MDP. The second step is that we solve this RM-MDP to get a conservative estimation. We call it Q hat. And the last one is that we design 2 regularizers and use these regularizers to regularize the online learning. Yeah. So yeah, let's go to the first step. We denote the direct graph as G, and the V here is the node. The node just contains one state, and the E here denotes the edges. The edges is just a transition that, as when we're at S, we take an action A and go to the next step S prime here. Besides this, we also just store some statistics on the V and E. For the V, we store the Q hat, just the estimation of the state action pair SA. And note here, we only store the action we have met. Like if there's an action that we never take in the environment, we will not just record this Q hat. And on the E, we just record the action, reward, and the and here is the visit count. Like we may revisit the same transition several times, so we count this number, and then we can estimate an empirical transition probability here. Yeah. So when the new transition comes, there are several cases that we when we build this graph. The first one is that if this, like this orange one, if this transition already in the replay memory, we just update the visit count here, right? So since it is the same, we don't need to add the new node at the new edge node. So the next one is that if this transition does not exist, so we will create new node and new edge for this transition. So we put it here. And there are more complicated cases like here, like when the ST exists in the replay memory, but ST+1 does not. So in this case, we update the visit count for the ST and create new node for ST+1 and also this edge. So the main idea is here, if we know one transition in the replay memory, we just update the statistics. If it was not in the replay memory, we create a new node or create a new edge. Yeah. And then after that, we can just estimate empirical transition probabilities here P hat. Okay, so with all these items here, we just have this empirical MDP, this RM-MDP. Yeah. Okay, so the next step is to solve the RM-MDP. Here this equation is similar to the one that's used in Q-learning. The only difference is that there is a constraint when we take the maximum operator. So here is just to say when one action has never been taken when we collect the when we interact with the environment and form the replay memory, we will not consider that value. So it is a conservative estimate. Yeah. There are some ways to update the Q hat. The simplest way is that we just update the whole replay memory during each step when we interact with the environment. We call it sweeping update. But obviously, this way will cause a lot of computations. So simplified way is that we can just sample a batch of data and update the Q hat. So this is similar to the original DQN. Since DQN will also sample a batch, we use the same batch to update the Q hat first, and then we update the Q network. And also here I didn't write here, like when we just interact with the environment and an episode ends, we also update the episode in the reverse manner. So this sampling just also includes the idea that experience replay with reverse update. Yeah. Here is a picture that we show this sampling update can get the similar performance as a sweeping update. So let's say even though we didn't update at each time step, the performance is just that is enough. It's accurate. Yeah. Okay, so the last step is to design the regularizer and regularize online learning. So first is value regularizer. So here the main point is that when we compute the target value, we besides the TD learning that bootstrapped from the Q network, we also use the Q value that's derived from the replay memory. So just a combination of the two terms here. Since the Q is like a TD learning objective, but the Q hat here is more like a supervised learning objective. So it's also consider the episodic IO in this objective. And also since the Q hat is only derived from the replay memory, so it will not so likely to overestimate. So it's also a good complementary for the Q value from the Q network. Okay, and then about the policy regularizer, since the goal is to learn a good policy, so the more straightforward way is that we can add a policy regularizer on it. This way is also simple, like we just use the softmax function to derive two policy from Q hat and the Q, and then we use KL divergence to make the two policy just close to each other. Okay, and then we combine the two losses together, and this is the final object learning loss we use. Yeah. Okay. Okay, so this is the pseudocode for our algorithm. It is pretty similar to DQN since we just combine our methods with DQN. Yeah. So first we just initialize the replay memory, and this replay memory is also have the fixed memory size. I'll say that like the previous DQN is the first in first out queue with fixed memory size, and our memory is just a first in first out structure, a directed graph with also fixed memory size. Yeah. The only difference is that our memory is a structure. Yeah. Okay, and then we initialize the Q network and then interact with the environment and take action. These all things are just the same as DQN, and save the transitions in the replay memory and update the statistics. And we sample a batch. And before we update the Q network, we first update the Q hat in the replay memory, and then we update the Q network. Just this procedure repeat. Yeah. So Okay, so let's go to the experiment. First, we show an experiment on the toy example. It's cliff walk. The goal is to start from the starting state S and reach the goal state G. The reward is just when we reach the G, we will have a 1. Otherwise, the reward is 0. And if we fall into the cliff, the reward is -1. Okay. So there are some baselines. The CEER is our method. And the Q-learning here is the tabular method Q-learning. Since this environment has a small state action space, we can just use the Q table to know the policy. The DQ is just Q-learning with neural network and experience replay. The only value is that we only add the value regularizers. And the only policy is that we only add the policy regularizers. The first picture shows the performance, and the second picture shows the Q value error.
Off the cliff, do you stay falling down, and you climb back up afterwards?
Episode N.
Episode N?
Does the episode end when you fall over? You fall into the cliff?
Yeah, there is just a limit of the max step. I think I set it to 120. Okay. So yeah, even though it cannot go to the goal state, it will end when we reach the.
Climb out of the cliff.
Climb out of the cliff.
What is it? The end of the episode.
Yeah. When he also fall in the cliff, this episode will end. So there are conditions. The first one is that it fall in the cliff. The second one is that it reach the goal state, and the last one is that it's reach the maximum steps. Yeah. Okay. Okay. So the first one we can show that the DQN that does not work within only 100,000 steps interactions with the environment, since maybe because it uses a neural network and there's some error, but also some generalization. But in these cases, the generalization maybe doesn't matter because the action state space is pretty small. Yeah. And then we can find the Q-learning works pretty well. Since this is just a tabular case, so it works well. And also we can find the if we add the policy regularizer, it is better than the only add the value regularizer. But from here we can say that the policy only if we only add the policy regularizer, the Q value error will be larger than that's when we only add the value regularizer. So here we want to show that the two regularizers just play different roles, but they all benefit the learning. Yeah. Okay. So here we show the overall performance on some more complicated environment. We test our algorithms on 3 kinds of environment. So the first one is scoop-on. The scoop-on is just we need to push the box to the right locations. And the second one is the mini-grid. The mini-grid is just they implement some tasks in the grid world. For example, in this one, the agent need to first pick up the key and then open the door and finally reach this green square. Yeah. These 2 kinds of environment is also sparse reward. Like only when they finish the game, they will get a positive reward. Otherwise, they will get a small negative reward to penalize the steps that they used. Yeah. And the Miyata is just a simplified version of Atari environment. The mechanics are almost the same, but the input is much more simpler. Yeah. And then we can find on most of these games, method just works pretty well. Yeah. It's just the reward, the cumulative reward. Yeah. Okay, so then a later question is that in which circumstance our methods will work and in which circumstance will our method does not. So here I designed a metric called ARPI. So it's just a performance improvement compared with baseline method. Here we compare with DQN. the score here is normalized with just less than or equal to 1. Here the higher score means the performance improvement is higher, and if this score is less than 0, it means the performance just decreased. Yeah, and I also designed another metric called memory density. The memory density is just to measure if the graph we built is dense or sparse. So it's just the out degree of the states. So it just means if at one state we only have one action, so this sparse will be, or this graph will be pretty sparse. But if at one state we have many actions have been tried, so this graph will be dense. And then we draw a picture here like this. We can find if the replay memory is dense, we can find a large performance improvement here. So this is a strong correlation here. Yeah. And okay. Finally, we do a ablation study here. Since the previous two example didn't consider the memory density, so here we'll just do the ablation study across different memory density here. Here we want to show that across different density, what's the role of the two regularizers. So first we look at the value regularizer and the policy regularizer. We can also find the policy regularizer just pay more importance roles on the performance improvement. So like even though the density is small or the density is large, yeah. And actually we also do another experiment. We call it conservative policy. So this conservative policy is that we directly nerf from the replay memory, right? Since we already have a Q hat estimated from the replay memory, then we can just use the supervised learning to nerf from the Q hat. Yeah, this one is similar to that. And then we can find when the memory density is small, this conservative policy just pretty bad. But when the memory density increases, we can find this conservative policy just pretty well, and even it is already better than the DQM. Yeah. So here I want to say that this result is very similar with this. Why this regularizer help? That is because when the memory density is high, the policy that's just in the replay memory is already a good policy. So when we use it to regularize the online learning, it will get a better performance. Yeah. Yeah, that is what we get from the conservative policy here. Okay. Okay, let's summarize our work. It's only half an hour. Okay. So in this work, we just consider the replay memory as an empirical MDP, and we call it replay memory MDP. And then we can solve this MDP and get a conservative estimate that we call it Q hat. And based on this Q hat, we design two regularizers. One is value regularizer and another is policy regularizer, and use the two regularizer to accelerate the online learning. Yeah. And from the experiments, we can find CEER just improve the performance a lot across different environments. And we find a strong correlation between the performance improvements and the memory density. Yeah. And also there are some future works we just plan to do. The first one is that since in this work, we didn't just design a state abstraction method to merge the state. We just check if this state is the same. Then if the same, we merge it. Otherwise, we just create a new node. But yeah, one way is that we can design a representation function. This function can just make some abstraction about the state. And then when we merge the state, there is a high chance that we can merge more states and then improve the memory density. And if we can improve the memory density, we can just get a higher performance. Yeah. And the other direction is that since we will build the graph, and the graph, we need to use the action to build the edge. So it is only suitable for discrete action space. So one other direction is that we can extend this way in just continuous action space or even continuous state space. Yeah. We have some just promoting directions, like since there are many offline IO methods that try to solve the empirical MDP. So maybe we can just borrow some method from the offline IO and yeah, use that way to estimate the empirical Q and use the empirical Q to regularize online learning. Yeah, maybe. Yeah. Okay, thanks.
I have a quick question. Should I go ahead?
Yeah.
So you mentioned that you have some ideas from the empirical RL literature about what can be done when let's say, even the state space is continuous, right? Like even in, I don't recall the state space of Minotaur, but like if I imagine some domains where, let's say, the numbers are some real numbers between 0 to 1. So in that, how would you build the graph? Like, how would you compare if two states are the same? Because it's very likely that no two states will ever be completely the same, right? So do you have any ideas of how to do something like this in that case for continuous?
Yeah, thank you for the question. I think one way is just use some offline method to estimate the Q hat. Since if we want to build a graph, even though there is just small difference, it will create a new node. So in this case, it's just like this kind of environment, like freeway. The memory density is just near the 0, so that means the trajectory just can't merge. So even if we build a graph like this, in fact, that's just a first in first out Q. So it just degrades to the DQN case. If we want to just tackle that problem, I think, yeah, just like we say, one way is that we can use an offline method. Since offline method, we just can sample the data from the replay memory, and then we just follow the equation 4 to update the Q hat. So in this case, it doesn't matter even the state is continuous or the action is continuous. Yeah, and I know there are some methods like implicit Q learning and in sample actor critic. This ways I'll all try to solve this equation. Yeah, so I think that may work. Yeah.
I see. So then instead of creating explicitly an MDP, just sample like a mini batch or something from the buffer, and then use that to create this conservative value estimates.
Yes. Since the purpose is just to estimate this Q hat, so this doesn't matter if we just use sampling method and do not build a graph. Yeah.
Okay. Yeah. Thanks.
Okay, maybe I'll ask a question.
Okay.
So when your density is low and it doesn't work so well, could you turn it around and say, okay, let's just sample more actions from those states and increase the density? Would that make sense, or would that be a bad idea?
So you mean we use a large replay memory, use a memory with large size?
Well, in this case, you're only indirectly affecting which states and actions, which transitions are sampled, right?
Yeah.
But I wonder if you look at it and say, okay, this state really only has one action. Let me change my sampling policy and sample some of the other actions as well. Would that make any sense, or would it just be too expensive? Or do you have any?
If we have a perfect model, if we can just reset the environment to exactly that state, I think we can. In this environment, we just reset the environment, so this state may not be the state that we want to sample another action from. So, yeah, I think if in something like board game like Gomuku, we can do like that.
Okay, thanks.
Yeah, but if we use this way in the like a Atari game, yeah, maybe, but yeah, since I think we just code base, we can just deep copy that environment and reset the state to the state that we want. Maybe in practice, just like in the real world, we cannot just reset to that state. Yeah.
Okay, I have another question.
Okay.
Sure. So can you give a rough idea of how much computation per step is required for this method? Like, for every environment interaction that you're doing, compared to DQ, and how much extra computation is done per step?
Yeah, I compare it in the appendix, and I find this way is just similar to the PER, the parameterized expression replay method. Yeah, so it's the time is just between 1 and 2 times of the DQ. So yeah, it's similar to the PER method. Yeah.
Okay, good. Yeah, thank you so much.
I have a question about the memory density. So you show that with a higher memory density, the performance improvement is also higher. Is it because you have a more accurate estimate about the Q values or something else?
I think yes. Since if the density is high, so that means that there are many trajectories that interleave together. So if we interleave together, and we can get a more accurate estimate for S state, since there are. So it's more like a tree structure. Like, yeah, we have some bootstrapping from many states. So yeah, maybe this way can get a better estimation.
Okay, thanks.
Okay, any other questions? So let me know.
Thank you.
Thank you so much.
Thank you.